All right, and if you go to the Canvas webpage and click the file section, the lecture notes are already there. And on top of the lecture note, there's a YouTube link. If you click that, you should be able to watch it, the recorded video, in case you miss a class or just want to review the lecture. I also uploaded the handwritten notes, which is what I wrote here on my iPad. You can also see a copy there, electronic copy there as well. Okay. Oh, there's one thing I want to sort of just briefly mention. Some of you might know this already. We have this, it's called the Quantum Engineering Fellowship. The former name is actually the National Science Foundation National Research Traineeship Fellowship. It's called the NRT Fellowship. We actually got this $3 million grant a couple of years back. And now we are basically trying to, use this money to support especially students in the quantum engineering master's program. I know a lot of you are actually enrolling in that program. Of course, we wouldn't be able to support everyone. We have a lot of them. A lot of you, recently, we only be able to support like probably at most 5 students a year. And this fellowship is a 1-year funding with possible extension to another year. But we only be able to support 5 students a year. So it's certainly going to be competitive, and it's mainly targeted to students who are actually interested in research and kind of already are ready to do research with one of our quantum faculty. We have a lot of quantum faculty in our physics department, but also some in the other departments doing quantum-related, quantum information-related research. So if you're interested, you can go check out, our website. So let me just switch to the computer here. So if you go to quantum.minds.edu, and this is our quantum engineering website. I think most of you know this, but if you just click on the top, there's a QE NRT stuff there, and and this is the quantum engineering fellowship, and there's like I think there's a button. Where's the button? Yeah, program information and application. So if you click here, there's some detailed information. You can expand here what this is about, and this basically just provides financial support, and it's a $34K stipend plus travel support. And there are requirements here. So you have to be a U.S. citizen or a permanent resident. So that's required by our funding agency. And there's a program here. Of course, you need to finish these courses. I think most of you are probably taking a lot of them just for the degree. And then you can do the application here. I think this round the application is probably due. Yeah. So the spring, the fall admission is actually due on the 20. Actually, this one is already passed. But I think we kind of, I don't think this is updated. You can still apply it until February, end of February. So, just do it as soon as possible. So if you apply now, you can get a funding starting either the summer or fall. But the important thing is, if you really want to apply this, you need to write a research project. So you need to talk to some of our quantum faculty to actually, have a plan of what you're going to do. If you're just not ready for research, this is probably not ready for you. I know some of you already got this fellowship in the previous cycle, and we are still open to applications, this spring. Any questions for this? And also, if you're just interested in my group's research, you can come to my group meeting, which is every Thursday at 9 a.m. in the CK 381, the small room on the 3rd floor of Course Tech. Or you can just talk to me after the class if you're interested in doing research with me. All right. Okay. So let's get started with where we left. So last time we talked about describing a quantum antibody state. So today we're going to talk about describing operators in a quantum antibody system. So this is our topic 1.2, describing operators in a quantum many spin system. We're still going to focus on spin systems, and if we have time, we'll talk about the system of many bosons or fermions. If not, we'll leave that to Wednesday's class. Right now, we are still just focusing on spin degree of freedom. Forget about whether the particles are moving or not. Okay, so last time we talked about how to describe a many-body state. We talked about this many-body wave function, which basically has d to the n components. If you have n qubits or n spin edge systems. And here we're going to talk about, of course, operators, because these are sort of the two mathematical objects to describe quantum many-body systems. Of course, if you have an unQDS system, then you would expect the Hilbert space dimension to go as d to the n, and then a generic operator A is going to be represented by a d to the n by d to the n matrix. So we denote it by this bold matrix, bold letter A here. It's kind of hard to write it here. We can still use this basis we introduced in the previous lecture, which is basically this natural basis or computational basis for unQDS system. So this is basically the vector S basis we talk about, which is also which basically stands for S1, S2, all the way to Sn. And we talk about what this means is actually a tensor product of the basis state basis vector for each qubit. Right? For qubit, just think about each of S taking value of either 0 and 1. For qubit system, it can be 1, 2, 0, 1, 2, all the way to d minus 1. Right? So you can take d different values. So that's a basis we're going to use. And in this basis, you can expand this operator A. This is an arbitrary operator A as a matrix in this following way. So I'm going to use this vector basis notation just to simplify things a little bit. So this is going to be my A, S, S prime, and then we will have S and S prime. So it's a usual outer product for denoting an operator in a basis, as we did in quantum mechanics. And here, the difference is that these indices, these are the row and column indices of the matrix, but these indices are actually, represented by a vector or a bit string here. So that's this S here. Of course, if you actually want to write out a matrix, for example, in your software, then these vector indices, you have to linearize it, which is actually not something so complicated. So for example, when we are talking about, an example of just say 2 qubits, then we know these basis vectors, this vector S will have 4 different, values. That will be, 0, 0, 0, 1, 1, 0, and 1, 1. Right. So each of this S or S prime will take one of the 4 different values. And then, we have to, in order to actually write it as a 4x4 matrix, we have to do a linear map of these indices into 1, 2, 3, 4. Right. So we basically just do a mapping here. And then you can basically write a matrix like A11, A12, A13, A14, all the way to, A44. Right. So you can basically write a matrix in this way by using a mapping of the basis from this sort of S1, S2 to Sn basis to the linear basis, which just goes from 1 to d to the n. And then mapping, usually you can write a simple code to do this in MATLAB or in any other software you want. All right. But this is kind of like the most naive way to write a operator in a many-body system. It's certainly not efficient because, if you look at the way we specify the operator, you need this d to the n by d to the n matrix, which just takes, just a lot of storage at the very minimum. But it turns out that most of the operators we're going to, deal with in a physical quantum system are not that generic. It's not like this generic matrix d to the n by d to the n matrix. Usually we're going to deal with operators that can be represented in a much simpler way. And these operators are called few-body operators. So what does that mean? So the idea is that usually if you have a n-particle system or unQDS system, then the operators we're going to be talking about, at least most of the time, the operators describing the Hamiltonian or the operators you are measuring, which correspond to the physical observables we're interested in, only acts non-trivially on a small number of particles, a small number of qubits here. In this case, this is called a few-body operator because the operator only acts on a small number of particles in the system. And for all the other all the other particles is just do nothing. It's basically an identity operator. So for example, if we talk about an operator, say, let's say a spin operator SIZ, right? So if you write it in this way, so this is a spin operator, for spin 1/2 is just it's related to the Pauli operator. It's a spin operator in the angular momentum operator in the z direction, but I put a subscript here which is I. It denotes that it's acting on the spin I. So it actually represents the spin angular momentum operator in the z direction for the particle I, for the spin I or for the qubit I. And in this case, this operator is not acting on the other particles, right? In this case, this is a very typical single body operator. And this operator itself, it's just d by d, right? If you think about spin 1/2, let's just, for simplicity, we just write it as a sigma iz, the Pauli operator. So that's for qubit. Just focus on qubit. So this is just going to be a 2x2 matrix. But of course, if you want to represent this operator for n qubit system, then you can't use a 2x2 matrix. You have to use this 2 to the n by 2 to the n matrix. So what you're going to do is to do a tensor product of this operator with identity on all the other qubit. So you put identity to the left of it and to the right of it. And remember last time when we were talking about the tensor product, it has a particular order, right? We always align our particles from 1, 2, 3 all the way to n. So basically, this is for the first qubit, this is going to be for the second qubit, this is for the ith qubit, and all the way to the nth qubit. So each of these identity here will be, corresponding to a particular qubit index, and then the sigma iz is that sigma z operator is basically, appearing in that ith position. And actually, in this case, we can forget about the subscript I here, because it's just a 2x2 matrix when we're doing here. The sigma z is just going to be this matrix of 1, -1, 0, 0. And each identity, of course, is just a 1, 1, 0, 0. Right. So this is basically how we represent this single body operator as an operator, as a matrix in the full Hilbert space dimension. And once you do this tensor product, you will get a 2 to the n by 2 to the n matrix. So this is how we actually represent it. So this is kind of like a more, if you just think about it, writing this full matrix is kind of like a waste, because the only information is carried by, the only useful information is carried by this sigma z. All the other qubits just get an identity. So this is the reason why people just often just, have this abbreviated notation that this is just equal to sigma iz, right? So this is kind of like just, it's just defined, it's kind of like a definition. Right. So if you see this notation sigma iz or any other operator on the I side, what it really means is to have a sigma z on the ith qubit and the identity on all the other qubit. Okay, so that's the case for a single body operator. And to make it a little bit more non-trivial, let's also talk about two body operator. These are much more important. And just to give an example, taking the same example here, I can have actually a sigma iz, sigma jz. So this looks like a product of two operators, but what this actually means, this is again a shorthand notation. What this actually means is you have a sigma z on the ith qubit and a sigma z on the jth qubit, and then you put identity elsewhere. Again, you still label the, you still do this 1, 2, 3 all the way to n. And then on the ith and jth qubit, you insert sigma z there. So this is how you do it. Okay, some of you might not be familiar with how we do tensor product for matrices. So I want to also, just mention how we do that. It's kind of very similar to how we do tensor product for the state vectors, which we talked about in the last lecture. So just to give you an example, you have two matrices. A is equal to, say, A11, A12, A21, A22. Right, so we're just talking about the 2x2 matrices here, so for single qubit. And then how do we calculate this tensor product? So if you have A tensor product B, then what's going on is you put A11 here, and then you put the whole matrix B here. And you do similar things for all the other one. and then you have A21. And the next part you do is to multiply these leading prefactors into those 2x2 matrices and just expand. Then you are going to get a 4x4 matrix instead. I'm not going to expand it because it's just a waste of time to write this. But then if you expand it, you are basically going to get a 4x4 matrix. This is how you do tensor product. And again, you can see that this does not commute. If you do B tensor product A, it will be different from this result, similar to how we find that out for the two quantum states. So any questions so far? Oh, yeah.
So when you say qubit, is that a qubit with more than 2 levels?
Yeah, so qubit is basically a qubit with D level. It's a generalization, right? Qubit has 2 levels, qubit has D levels. So we label them by 0, 1, 2, all the way to D minus 1, like right here, right?
Great,
so,
thank you.
Yeah. Okay, so if there are no questions about the tensor product, I want to give you a small in-class exercise to just make sure everyone knows how to calculate the tensor product for 2 matrices or for 2 operators. So let's calculate the tensor product of sigma x and with sigma x itself, where the sigma x is the Pauli operator in the x direction given by 0, 1, 1, 0. Right? You can use the equation I just talked about to calculate this. I'll give you a minute to work on this. All right. Any volunteers that can tell me the answer? Yeah. What about you, Aaron?
The shortest way I can describe it is like an identity matrix where the diagonal goes backwards.
Anti-diagonal, right? So yeah, that's right. Yeah, so it's like this. Yeah, how many of you get this? Can you raise your hand? Okay, great. I think most of you get it correct. That's great. Then you know how to calculate tensor product for operators. In practice, if you have a many-body system, you don't want to do this by hand, right? So this is just one little exercise. If you want to do something like this, it's going to take a lot of time. Fortunately, usually we use a software to do this. For example, if I'm using MATLAB to do the tensor product of 2 matrices, what you can do is to just we're just going to write it here. And just do crown of A and B. Right. So if you just do crown of A and B, it's automatically going to give you that final result. So you can always do that. You can also do the same thing for the state. Right. This A and B can be matrices, but they can also be the state vectors. Okay. So this is basically how we represent a single body operator and 2 body operator, and similar for 3 and 4. So what's really going on is whenever you see notations like this, right, it's basically like you have sigma z on the I and j qubit, and the rest of the qubit will just have identity. You just do this string of tensor product, and then you will get the matrix you want. But representing the matrix, the operators in this way is much more compact, right? So instead of writing this as a 2 to the n by 2 to the n matrix, you just write this very simple notation here, sigma iz, sigma jz. It's just much more compact way to do it. If you want to do calculations, you still have to do that for tensor product, right, in your software in order to do it. But at least, in terms of the notation, this is a lot easier. Okay, and so since we're talking about two-body operators, and the reason why they're important is because these actually correspond to physical interactions. So if you think about sort of the fundamental type of interactions of particles in nature, these are, we talk about these sort of 4 different fundamental forces in nature. If you sort of know physics better, you probably know these sort of 4 fundamental forces in nature, like, electromagnetic interaction, like this, weak interaction, and so on. And most of the interactions we're going to deal with come up from this electromagnetic interaction. And usually, the simplest example is a Coulomb interaction of 2 charged particles, right? And then in that case, we basically have a two-body interaction. So most of the physical interactions turns out to be two-body. What that means is that if you look at the interaction energy or the potential energy of the 2 particles, right? This can be any 2 particles, but it always takes like this pairwise form, like xi and xj. Here, for Coulomb interaction, the xi and xj just denote the position of the 2 particles. For example, so this is Coulomb interaction. Then this goes as something like ei ej over the distance xi minus xj, and these can be vectors. Right, so that's basically the Coulomb interaction between 2 charged particles. And the Coulomb interaction actually also give rise to the interactions between the spins. So it's kind of also electromagnetic interaction. If you have 2 spin angular momentum, you can think about the spins as a magnet, and they will basically have dipole interactions between them. So in this case, if you look at the interaction between 2 spins, let's call it Si and Sj, you will typically have interactions that looks like Si dot Sj, and this is a case which is called the Heisenberg interaction. Kind of comes from the 2 interacting magnets, right? When the 2 magnets are aligned or they're anti-aligned, the energy of them will be different. The dipole interaction is a little bit more complicated. Yeah, I think it goes like, it's kind of related to this Si dot Rij, and then you have Sj dot Rij, and then divided by Rij cube. So it's kind of related to the inverse of the distance, and these Rij's are kind of the unit vectors along the the direction of the 2 particles. But the actual form of this is not that important. Usually when we're talking about the dipole interaction, we kind of project this onto a lower dimension, and then it becomes something like an XXZ type interaction. Usually it reduces to something like Si x Sjx plus Si y Sjy. The S are just the angular momentum, and then plus some coefficient delta of Si z Sjz. And then you have some coefficient Jij in front of it, which is kind of related to this 1 over R Ij cube. And the delta here is related to the angle of the spins made with the direction of Rij. So typically the dipole interaction gets reduced to this type of interaction. Typically we call it XXZ interaction because the X and Y directions have the same coefficient, but the Z direction's got a different coefficient. So this is typically called the XXZ interaction. And for the spin interactions, there's also like an even simpler interaction, which is just the interactions for a particular direction of the spin, and that is called the Ising interaction. For real physical systems, Ising interaction is kind of rare because why the spins are only interacting, in a particular direction. But in some very particular case, in some real materials, some very specific real materials, you might get interactions close to an Ising interaction, like the interaction is only dominating in a particular spatial direction. But much more commonly, the interactions among the physical spins, like the spins the electrons are carrying in a real material, are given by the Heisenberg interaction or the dipole interaction. So, in general, the physical interactions we get for actual particles we have in a quantum system are going to be two-body. So you basically just have every 2 particle interacting, in a pairwise way. Of course, every I and j you need to sum over, right? So the real Hamiltonian is going to be a summation over I and j, and you take these v's, it's, for example, vsi, sj, or the xi, xj. So it's always the sum of all these pairwise interactions. So this is why two-body operators are very important, because most of the physical interactions we have are two-body. This doesn't mean that we can't have more than two-body interactions. We can have, for example, four-body interaction. For example, we can have an interaction where this interaction is given by an operator like SIX. I'm just writing a random one: SIZ, SJZ, SKZ, SL. I just put an X here. It's kind of, just give an example. You can't have a four-body interaction like that, but it's very rare to get it naturally. And in order to get these four-body interactions, usually you have to engineer them. There are ways to do that. Typically, it's because like the fundamental interaction is two-body, but if you do some kind of perturbation theory, then in the second order perturbation theory actually becomes fourth order. Yeah, question, Richard.
Is that supposed to be SIX, SIY, or is that SIX?
It doesn't really matter. I'm just writing a random one. These directions, you can write anything. I'm just going to write, you can write all these, but it's kind of random. I'm just giving you an example. If you actually see a notation like this, you have four different subscript, which correspond to, spin operators on different, spins, then that's a four-body interaction. Question, Bora.
Yeah, for the interaction you wrote,
Mm-hmm.
it's written as XXZ.
Yeah.
Right hand side.
Yeah.
XYZ.
Yeah, it's XYZ, but the X and Y have the same amplitude. So people call this XXZ. Just, if you call it XYZ, typically it means that these three interactions in three different directions can have different values. If they're the same, X and Y are the same, they're denoted by XX. It's just kind of like convention. It's a good question. Yeah. Yeah, but the physical origin of that is just the dipole interaction. Yeah, question. Yeah.
You said most physical systems are going to be two-body.
Yeah, it's going to be two-body interaction. So every two particles interact, and you never have three particles interact together. They always interact in a pairwise way.
What's the application of engineering these four-body interactions?
Yeah, that's a very good question. So these four-body interactions sometimes can give you some very interesting properties. So later on, when we are talking about topological order, there's a very famous model called the Kitagi-Tori code, which is also related to error correction code, that actually has only four-body interaction. So the Hamiltonian is made of pure four-body interaction terms. If you only have two-body interaction in Hamiltonian, you cannot actually get to that particular topologically ordered state. Yeah. So that's why it's very hard to engineer it. Nobody actually has achieved it, at least in a large scale. Some people did some demonstration experiment with 6 photons. You can get these four-body interactions. But typically, it's very hard to engineer them. And for most cases, we're just going to restrict ourselves to two-body interactions. Any other questions? Good ones. All right. And of course, if you have a quantum simulator, usually you can engineer the two-body interactions very well. Like in this case, the XSZ interaction. In some platforms, you can actually engineer the delta very well. You can tune the delta to what value you want. You can also make the Jij kind of almost arbitrary. You can make any arbitrary, interaction pattern in some platforms. For example, trapped ions can do this very well. So that's the idea. But usually it's limited to two-body interactions. Okay, so the other thing I want to talk about is that, few-body operators are represented by sparse matrices. So this is a very important observation. So if you have a few-body operator, either it's a single body or two-body, these are the most two common things we're going to talk about, like these two things we just talked about here. Then these operators, if you write it in this computational basis we talk about, your exercise here, right? So here we calculate this one. So that is a two-body operator, although we only have 2 qubits. So it's kind of a little bit trivial. But in general, these operators are represented by sparse matrices, which means the number of non-zero elements is only a small fraction of the total number of matrix element. And typically, the sparsity of a matrix is defined by the number of non-zero matrix elements per row. So if you look at each row, then you count how many non-zero matrix element you have, right? Of course, if each row has this number is different, you usually take an average, you know, this can go as as large as 2 to the n, right? As d to the n, if you have that row fully filled in. But if you're talking about a sparse matrix, typically this number will only be polynomial in n, if you're for like an n, qubit system. So that's what a sparse matrix actually mean, right? So if it's not sparse, then typically it's exponential in n, right? It could be d to the n, it could be some constant factor times d to the n. But as long as it scales exponentially, usually that's not a sparse matrix. But if this number only scales polynomially, polynomial could be either a constant or is proportional to n, or it could be proportional to n squared. So anything that can be represented by a polynomial, we call that polynomial scaling. I typically just use this notion of poly here. It's a very common notation in complexity theory. All right. So to give you an example, let's try to think about this. So let's just say we have a simple operator A that is just equal to sigma ix. We just talk about what this actually means. This means it's basically a Pauli matrix sigma x on the ith qubit, and then it's going to be identity on all the other qubit, right? So we're talking about an n qubit system for an n qubit system. So let's try to represent this A in a matrix, and then we know that this is going to be just identity, on all the other qubit except sigma x here, and then you have identity on the rest of the qubit, right? So you're going to get a big matrix here, and now I want you to think about this question here. So how many non-zero matrix element we have per row? For this above matrix A, for this matrix A here, and this will take a little bit of thinking. So I'll give you a few choices, 1, 2, n, and then you have something else. Yeah, let's also put an E here, which is basically I don't know, and then we can use the clicker to do a poll on the answer of this question. Yeah, just think about it. Of course, you can do that calculation, but it's going to be complicated. But just think about it. What do you think? How many non-zero matrix elements will there be for this operator sigma ix? There are multiple ways to think about this, or you can just make an educated guess. All right, so I'm going to open a clicker question. Okay, if you have the answer, you can use your clicker to choose it. We have A, B, C, D, E here. All right. Looks like most of you have made the choice. I'm going to review the answer. And yeah, I think the majority have the correct answer. So the correct answer is indeed A. So there is just one non-zero matrix element per row. And there are a number of ways to see this. Of course, you can just look at just do a calculation, for example, for 2 qubits and see it. But the easiest way to see this is to know what the sigma ix is doing, right? So the sigma ix, when you apply it on a basis vector S1, S2 to Sn, this is just one of those 2 to the n basis vectors, right? What it is doing is to flip the ith qubit. So what's going on is all the other qubit, the s values are intact, but if you look at the si, it changes to 1 minus si. Right, it basically flips the ith qubit. So if the si is equal to 0, it becomes 1. If it's 1, it becomes 0. So the sigma ix is doing that. And you can also see that just from the matrix is, representation of it is given by this, this one. Oh, where is my sigma x matrix? That's given by this matrix here. All right, if it's doing that, that basically means per each row of the matrix, we're basically looking at how it's transformed. You only get one non-zero element, so it goes to that, right? So if you, for each row, there's only one non-zero matrix element which corresponds to the row, to the column index given by this, and the row index given by this. So there's a unique combination of that. So you just get one non-zero matrix element per row. If this is not clear to you, we can look at a 2-qubit example. So if you're looking at, so let's say I is just equal to 1, just for simplicity, right? It doesn't really matter because if you choose any I, the problem should be symmetric. So if you do sigma 1x, then we have 4 basis states, right? So you are just going to look at the 0, 0 here. And then this is just going to give us 1, 0. And similarly, we can look at sigma 1x on the 0, 1. And this is going to give us 1, 1. And sigma 1x acting on 1, 0. This is going to give us 0, 1, 0, 0. And sigma 1x acting on 1, 1. That's going to give us 0, 1. So you just flip the first qubit. And then if you write this as a matrix, all the other matrix elements are actually 0 because it doesn't actually connect, right? So if you write it as a matrix, as a 4x4 matrix, indexed by 0, 0, 0, 1, 1, 0, and 1, 1. And this is my 0, 0, 0, 1, 1, 0, and 1, 1. Right. So what's really going on is this, the 0, 0 goes to 1, 0. So we basically just put a 1 here. And the 0, 1 goes to 1, 1. So we put a 1 here. And then the 1, 0 goes to 0, 0. So 1, 0, and 0, 0. So there's a 1 here. 1, 1, and 0, 1. So that's, a 1 here. Right. And then you basically put 0 everywhere else. You can also do this using a software if you're lazy. But if you see this clearly, each row has one matrix element, right? So the 0, 0 gets taken to 1, 0, so there's a 1 here, and similarly for each other row. Right? Yeah. Any questions on this? All right. Okay, so this is just a single body operator, a sigma ix, right? So then it's kind of easy to generalize this. So for example, if you have a Hamiltonian, let's say it's just made of sum over I, sigma ix, then how many non-zero matrix elements do we have per row? Should be a relatively simple question. If this is the operator, we're trying to do a matrix representation, then how many elements do we have per row? Anybody wants to make a guess? So we just say for each operator, there's only one. And then there's a sum over I. Let's say I goes from 1 to n. Now how many do we have?
Should still be 1, right?
Is it still 1? Yeah? Anybody wants to? Yeah, we can think about this a little bit. Yeah. Yeah, what about I just make a 2-qubit case? Let's do sigma 2x here. Yeah, I'm not going to write the other ones. It's kind of similar. Right, so we can write a sigma 2x here. Then the 0, 0 goes to 0, 1. So if I want to write a matrix of sigma 1x plus sigma 2x, then for the similar one, I will still have the previous one, but now the 0, 0 also goes to 0, 1. So just looking at the first row, we have 0, 1, 1, 0. Right? The 1 is from the sigma 1x. And then the sigma 2x give me another one, which is 0, 1. So actually this will give us 2 non-zero matrix elements, right? And then if you have n qubit, it just goes naturally. So then you have n non-zero matrix element per row. And the formal way to think about it is if you have the sigma ix, this is going to flip the i's qubit, and for each I, it's going to flip one of them, right? So if you have a sum of them, then you are basically going to have a sum of this. So if you have a sum over I here, then you are going to have a sum over I here. And this is going to be n different basis vectors, right? Because each one has a different qubit flipped. So it generates a unique basis vector. So each one has a different one, so that's why you put, in this case, you put 2 ones here. So in general, you will have n different matrix elements if you have a sum of single body terms. Right? And similarly, if you have like a sigma ix, sigma jx, if I have a term like this, this itself only generates one non-zero matrix element, because what this does is, if you look at a particular basis vector S1, S2, all the way to Sn, it just flips 2 qubits, right? So we'll have the 1 minus Si and the 1 minus Sj here, and all the other ones are just unchanged. So you're still going to just get one different basis vector. So if you just have one of them, it only gives you one additional non-zero matrix element per row. But if you put a Jij here, and sum over I and j, here you can also put some prefactors here. It doesn't really make things different as long as the prefactor is not 0. In general, if you have a sum over the I and j here, then you're going to have basically n squared non-zero elements per row. It's not exactly n squared because you also have the diagonal terms, which goes to identity, and some of the terms could combine with the sigma x, but on the order of n squared is pretty close to n squared. Yeah, so yeah, question, Vince.
Earlier we did the Kronecker of two sigma x's, and we got that it was like the opposite diagonal.
Yep.
And then there was still one.
Yeah, it's still 1. So yes, that's what I just said, right? If you just have one of them, it's still 1. But you can have a sum of them, right? For 2 qubit, of course, it's trivial because the sum, yeah, it's just 1 and 2. There's no way you can sum it, right?
So if the Kronecker represents putting like a sigma x on each qubit, then what is the sum? I think I missed. What is the sum of two operators mean?
Oh, you mean what the sum is? So if you have, for example, sigma 1x, sigma 2x, right, plus the sigma 1x, sigma 3x, it's just a sum of two matrices,
Okay.
right? That's what it means. So what this means is like you have, so for example, we have 3 qubit. That's a good question. Let's just spell this out. So what this stands for is sigma x identity, plus sigma x identity, sigma x, right? Each of them is a 8 by 8 matrix, right? We have 3 qubit here, so it's 8 by 8. You just add these two 8 by 8 matrices. And if you,
When the scarcity became 2, what did that represent whenever you added like sigma 1x plus sigma 2x? Just in the matrix to the right of first matrix?
which one?
0, 1, 1, 0.
Oh, you mean this one? Yeah, this is sigma 1x plus sigma 2x. What it stands for is sigma x tensor product identity plus identity tensor product sigma x.
Okay. And then what is that like? When did we do that?
When do we do that? Yeah, so this is a case where you have a sum of single body terms in your Hamiltonian, right? And to give you like a physical idea, this sigma ix term could just represent the energy of a spin when it's in the magnetic field, right? If you apply a uniform magnetic field on all the spins, then you are exactly going to get a term, which is the sum of sigma x, right? And then the sigma ix, sigma jx, we just talk about these pairwise interaction. This is an example of a pairwise Ising interaction. And if you have this Ising interaction among every two spins in your system, and they have a different coupling strength, that's what you get. And we kind of talked about this before for applications. If you have just these two type of terms, it already can make a very powerful computer. So this is the next thing I want to talk about. So if you have a Hamiltonian that just is given by this Jij, sigma ix, sigma jx, and then I have another term that's just called sum over I, sigma iz. Let's just put it in the z direction. So this is exactly what the things we all talk about. So these are the single cubic terms. And thanks to Win's question, I think everybody knows. Everybody should know how we calculate this sum here. We just sum over these individual terms. And this is an interaction term. So if you just get these two terms together and make a Hamiltonian, this is called the transverse field Ising model. Transverse field Ising model. Yes, this model is very, very powerful. We're going to actually talk about how to solve this model later on when we are talking about quantum phase transition. You can't solve it in a very general case, but if this Jij here just denote a nearest neighbor 1D interaction, like if you just put all these qubit or these spin 1/2s on the string, and the Jij is only non-zero if I and j are next to each other. So when I is equal to j plus 1 or j minus 1, you set it to 1, and all the other is 0. For that particular Jij matrix, we can actually solve the ground state of this Hamiltonian exactly. It's a textbook model for quantum phase transition. But this, of course, gets more interesting if this Jij is actually arbitrary. So it's, you just put some random values you want to put. Finding the ground state of this Hamiltonian is actually a really hard problem. And in fact, just finding the ground state of this part of the Hamiltonian itself is an NP hard problem. So it's finding the ground state. And this is actually a classical problem because if you just have this Hamiltonian, then every term can be used. So the sigma ix and sigma jx, you can just replace it by 1 and minus 1, right? Because there's actually no need to use quantum mechanics. You just basically find the ground state in the diagonal basis of sigma x, and apparently this Hamiltonian is diagonal. This first term itself is a diagonal matrix, so you just find the classical problem setting each of the sigma x to be either 1 and minus 1. Well, what is the combination of the sigma x values that makes the sum minimal? And that is a hard minimization problem. It's an NP hard. If you add the transverse field term, what you can do is, this is the idea of adiabatic quantum computing. We can start in the ground state of this, and then gradually turn the Hamiltonian from this part to that part. So we can make an adiabatic change of the Hamiltonian. If you have these two, I can call this my H1. This is my H2, and then I can do a H. That is a function of some parameter S made of basically S of H1 plus 1 minus S of H2. You can change this S gradually from 0 to 1. In that case, the Hamiltonian changes from H2 to H1. And according to the adiabatic theorem of quantum mechanics, you will stay in the ground state if you go slow enough. That already gives you a very powerful application. It's called the adiabatic quantum computer. But the other thing I want to say is that in general, if you have a Hamiltonian with just two-body interactions, you can include the single-body terms. Usually that doesn't change the complexity too much. In general, if you just have two-body interacting terms, and you want to find the ground state of that Hamiltonian, that is already a very hard problem. And this problem is called QMA hard. So this is just finding ground state of a Hamiltonian made of just two-body interactions. So I just write a generic one. I just call it Hij. So Hij just denote one of the two-body interactions. It could be this IC interaction, but it could also be, these different interactions we talk about, right? It could be Heisenberg, it could be this dipole interaction. But as long as it's just made of two-body interaction, finding the ground state itself is called a QMA hard problem. So the QMA stands for quantum Mermin-Arthur. Yeah, the particular name is not that important. If you're interested, you can just search Wikipedia for what a Mermin-Arthur problem is. It's kind of interesting in computer science itself. It dates back to this sort of famous story on King Arthur. I think it's kind of related to the roles there. It's kind of a interesting problem. Like Arthur asks some question, Mermin wants to understand. But if you want to know the details, you can go there. I don't have time to talk about this. But it's basically just a very hard problem, even for a quantum computer to solve. And I want to actually show you sort of a nice picture on this. What does the QMA actually mean? So the QMA is a large class of problems which correspond to this solving the ground state of two-body Hamiltonians. It's a very large class of problems. In this case, it's actually given by the largest circle. So there are a lot of problems in those. You can see that the famous P and NP problems are believed to be just contained in the QMA. So first, just to clarify here, this whole plot here is only a conjecture. So nobody can prove this. If you probably know this famous conjecture of whether P is equal to NP, right? This is a sort of $1 million question. I think it's regarded as the most important question in the 20th century. There's like this 9 different questions. So P equals to NP is a very big question, and nobody knows. But most people believe that P is contained in NP. If you don't know what P and NP means, I have some short explanations here. So P contains all the problems that can be solved efficiently using a classical computer. So it's kind of the problems everybody likes, right? So if you just run it on a classical computer, you can solve it efficiently. Basically means the runtime and also the memory cost scales polynomially with the problem size, right? Which is great, right? Usually you want a low order polynomial, like linear or quadratic. NP, that's the next famous one. it's not like non-polynomial. That's a very typical misconception. You think NP stands for non-polynomial. No, it's actually not. It's actually called non-deterministic polynomial. But the actual meaning of that, we can forget about what it actually means by words. But it's just the class of problem who you can use the classical computers to efficiently verify the solutions. So you can check the solution. We don't know whether we can get the solution efficiently, but if you have the solution, I can check it efficiently using a classical computer. It's kind of a weird way to think about it. Question?
Is all this terminology specific to like solving quantum mechanics problems?
Not really. These P and NP are defined just for every computational problem human, we know, right? Like tribal salesman, right? Everything, like, just searching a database, right? These are very, very general. And I'm just going to put the quantum things just in a moment. And these other two classes, BQP and QMA, are less commonly known, right? At least not to most computer scientists, but the physicists sort of invented these two other categories. So the BQP is kind of a quantum generalization to P. Question, Bora?
Oh, yeah. Just want me to interrupt. Is it been approved to show that BQP is not contained in NP?
I'm going to get to that. Yeah, it's a good question, but it's a hard question. Yeah, so the BQP is like all the problem we can solve on a quantum computer efficiently. So it's a direct generalization of P, right? P is all the problems that can be efficiently calculated on a classical computer. So the BQP is going to be this yellow one here. And certainly we know that if you can solve a problem efficiently on a classical computer, you should be able to solve it on a quantum computer. The quantum is more powerful than classical, right? And in general, people believe that the BQP is larger than P. So that means there are problems that cannot be solved efficiently on a classical computer, but can be solved efficiently on a quantum computer. And one of the famous examples is the factoring problem. The Shor's factoring algorithm can solve the large factor, prime factor factoring problem on a quantum computer efficiently, but we don't know any algorithm that can do it on a classical computer. But keep in mind that this P containing BQP is also a conjecture. Nobody can prove that there are indeed problems that can be efficiently solved on a quantum computer, but cannot on a classical computer. Like even this, this prime factor, this factoring problem, we could argue that it's just we haven't found a classical algorithm that can solve it efficiently. You never know. It's very hard to prove that, BQP is actually larger than P. In other words, it's very hard to prove that quantum computer is actually, strictly mathematically speaking, more powerful than classical computer. Nobody can prove that, but almost everyone now believes. So that's the thing. Complexity theory is like a very hard branch of science. I actually know some of the very good computer science, complexity scientists, theorists of this age, and they all struggle. It's very hard to prove anything. yeah. But if the best they can do is something. It's kind of funny. They can prove something, basically saying that if this happens, then P is equal to NP. That's the best they can prove. So, and if everybody believes P is not equal to NP, then their proof is correct. So they have to basically count every proof on some assumptions that nobody can prove, but everybody believes. Because it's just crazy to believe P is equal to NP. So that pretty much means classical computer is also really powerful. You can solve the tribal salesman problem efficiently. So the tribal salesman problem is actually in NP. It's also called the NP hard problem. I kind of just mentioned that terminology for the IC model. So the NP hard problem is the hardest problem in the NP class. If you can solve an NP hard problem efficiently, then you can solve every other NP problem efficiently in that class. So people believe that the quantum P is going to be larger than the classical P, which is kind of easy to understand. And then the other question is, I think Bora just asked, you can see this BQP kind of overlaps with NP only partially. So this is kind of a very interesting point. So the first thing it means is that the BQP is not going to completely enclose the NP. So that means definitely we can't solve every NP problem on a quantum computer efficiently. And this is a general belief. Again, nothing can be proven here. It's just a general belief by the smartest complexity scientists in the world. If you try to use quantum computer to solve the tribal salesman problem, which is the NP hard problem, generally people believe that's impossible. The quantum computer cannot solve it efficiently as well. So don't have that dream. So that's unrealistic. So you can't count on the quantum computer to solve the hardest problem classical computers are facing. But on the other hand, it can also solve some problem that is even outside of NP. So that's also interesting. So what is that? So there are problems. So these NP and P problems are kind of like what is called decision problem, like you're basically asking a yes and no question. But there are also problems which is not just asking yes and no. An optimization problem actually is one of them. So you're basically asking, the algorithm to find the minimum. And there are also like problems called sampling problem. I just want to sample from a particular distribution. It's not a simple yes and no problem. So that's not called a decision problem. And the P and NP both are called decision problem. And there are problems not called decision problems. For example, some optimization problems or sampling problems that can be possibly solved by a quantum computer efficiently. And we also don't know any classical algorithm that can do that. So this is why we have this little sort of breach outside of the NP domain. So if you want to search for all applications of quantum computing, there's probably some problems that belong to NP and not P, and some problems that are not even decision problems. So that's generally the application here. And if you think about the QMA, which is basically the quantum version of NP. So these are all the problems where the solutions can be checked efficiently on a quantum computer. So that, of course, will include all the problems where the solutions can be found efficiently, right? Because checking the solution is much easier than finding the solution, right? Okay, so that's kind of the most important complexity classes for quantum computing. And I kind of want to mention this just for the fun of it. And finding the ground state is actually a really hard problem. Yeah, so if you remember in the last lecture, we kind of talked about these different ansatz, right, to represent the quantum many-body wave function in a compact way. And this doesn't really solve this. Even if you have an efficient ansatz, like we talked about, these neural network, this matrix product state that can represent some of the ground state of physical quantum systems efficiently, but it doesn't mean that we can find the ground state efficiently. So it's like if you have the solution there, it can be stored in an efficient way. That's the only thing it guarantees. And finding the solution is still hard. Even these sort of latest ones, like these neural network algorithms, it's not guaranteed to find the ground state of a quantum system. The best you can do is to break the record of the previous ones. Yeah, but nobody knows whether that's actually the true ground state. Yeah, of course, in this course, mostly we're going to deal with cases where we can actually find the ground state, because otherwise we can't have a good understanding. And these are, of course, only a very small class of Hamiltonians we can do that. So it's kind of like, in general, we're dealing with QMA problem, but we're looking at a very small type of Hamiltonians, which kind of belongs in that P class. Yeah. So, and then sometimes we'll talk about some slightly harder problems. Yeah. Question. Yeah.
So to clarify, you said that there's a set of Hamiltonians that you can find the true ground state
Yeah.
for, but people are competing with other Hamiltonians.
Yeah. So the hardest problems are QMA. QMA is a big class, right? There's certainly simple ones that's in the P, right? So and we are going to mostly dealing with those. Yeah. Yeah.
Is there one like Hamiltonian or set of Hamiltonians that people commonly are working on, or do you
like-
have to look at other papers and say I'm
Yeah.
going to try what they
It's a good question. Let's just talk about. Yeah, just for example, just for this IC model, right? If you have an arbitrary JIJ, like a random JIJ, that is a QMA hard. So it's basically the hardest problem in the QMA. And there's no way we can solve this efficiently. Whether analytically or numerically, there's no way to do it. But the ones we're going to do are simple ones. For example, the JIJ, it's just nearest neighbor. It's kind of like a tri-diagonal matrix. In that case, we can solve this exactly. Right? So that's the case. And that belongs to a P problem. Right? Yeah, any other questions?
Yeah, one
Yeah,
question.
Paul.
How is an optimization problem QMA? How can you check that you have?
Yeah, that's a very good question. I don't have time to go into that. So, yeah, so the way you deal with this is to ask the, quantum computer or classical computer, is this solution, right, forget exactly. It's kind of like you ask the question whether this configuration actually gives you energy below a certain threshold. Right, you find a solution which is basically the configuration of this sigma ix, right, whether it's 1 or -1, and then you ask the computer whether it's actually below a certain threshold, like for example below -10, and you can actually check that solution very easily. You just put in the values there, and you can do it. So it's not exactly,
You can prove you're better
Yeah, it can put it. So it's not even a yes and no question. It's in some sense it's a yes and no question, but it's like in a little different way. If you think about the minimum, asking the minimum itself is not a yes and no, but I can ask whether this value, this configuration keeps the energy below a particular value, and then you can lower that value, and you keep asking yes and no. Then you sort of, in some way, you can basically, change it to an optimization problem. Yeah. Okay. Yeah, that's a good one, but it's kind of hard to answer that one. All right. Okay, so we have a little bit of time left. We're going to start talking about, sorry. Oh, there's one more thing I want to talk about before we go to the next chapter. Okay, so we just talked about these few body operators, which are the most commonly used. And the other thing I want to talk about is that these are not only the operators that show up in your physical Hamiltonian, because most physical interactions are two-body, and single-body terms are typically like you apply a magnetic field or some kind of laser field that will generate single-body terms. Single-body and two-body, they are common. But also, if you are trying to measure a quantum system, these operators are also very easy to measure, right? So for example, if you're just trying to measure a single body operator, you can just do measurement on that particular qubit or particular particle. If you're measuring a two-body operator, sigma ix, sigma jx, you can just, measure those particular two qubits. So usually these few body operators, they're not only important for, for writing down the Hamiltonian, but also important for measurements. Most of the time we're measuring these. With quantum simulators, sometimes you can measure n-body operators, like an operator that actually contains n-body, which is not few body. But we'll talk about that later. So here, what I want to talk about is that based on this notion of few body operator, we can actually use something called an operator basis. So instead of using this basis of this computational basis to represent an operator, which is kind of very inconvenient, right? Because you basically need this d to the n by d to the n matrix to do that. So this is a computational basis, and this is usually inconvenient. And because most physical operators are few body, we usually use a much more convenient basis, which is called the operator basis. And for qubits, so for qubits, if you have just n qubits, these bases also have a name. It's called the Pauli basis. This operator basis is also called the Pauli basis. And this basis is actually something relatively simple. It's just given by the collection of sigma 1. We can call it gamma 1, sigma 2, gamma 2, all the way to sigma n, gamma n. And each of the gamma I here, we can take its value to be x, y, or identity. So each of these sigma here can basically be either a sigma x, or a sigma y, or a sigma z, or the identity. So you can take any of the four, possible values, and I basically use a gamma to label them. I can set gamma to be, usually it's not x, y, z, and I. Usually for convenience, we're just going to set it to 0, 1, 2, 3. It's just a way to label these four different matrices. I can call my sigma 0, sigma identity, sigma 1, 2, 3. I can just correspond to sigma x, y, z. And then you do a tensor product of all of them. So this actually just corresponds to a tensor product of sigma gamma 1, sigma gamma 2, all the way to sigma gamma n. It's the same notation here. So this is an n-body operator by itself, but we can use that as a basis for representing any operator. And this is actually true because if you just think about how many different operator bases we have, so this one has 4 to the n different basis operators. So there are 4 to the n different combinations of this, right? Because each gamma can take 4 different values. So in total, you have 4 to the n of them. And if you think about how many matrix elements I have in this, straightforward representation, I also have 4 to the n, right? It's 2 to the n by 2 to the n matrix. So I have also 4 to the n different coefficient. So any operator A, I can expand it using this new basis gamma 1, gamma 2, all the way to gamma n, as some coefficient gamma 1, gamma 2, all the way to gamma n, sigma 1, gamma 1, sigma 2, gamma 2, all the way to sigma n, gamma n. It's kind of similar to this. This is my coefficient. This is my basis, right? And I have 4 to the n different coefficient. So there are 4 to the n of them. So this is for n qubit. For q bits, it's kind of similar. You will get d to the 2n. Question?
Do we like drop the direct notation here?
Yes, you're talking about we're not putting hat there. Yeah, we're not putting hat. Yeah, we're just getting lazy. Yeah, you're right. Strictly speaking, we should put hat everywhere. Yeah, but I didn't do that through the entire class, so I didn't put any hat here. So it's just too much hassle to write the hat. So you know that the sigma is just an operator, right? Or you can think about it as a matrix. It's equivalent. Yeah. So this is called the operator basis. Question, Matt?
So is the sigma gamma only one of sigma x, sigma y, sigma z or identity, or could it be a product of like sigma x, sigma
No,
z?
it's only one of them.
It's only one.
So the gamma is either 0, 1, 2, 3, which correspond to sigma x, sigma. Let's write identity on the left. I usually like to use 0 to represent identity. So it's identity sigma x, sigma y, sigma z. Right. It's just corresponding to those 4 different values. And of course, the reason why we prefer this one is because this one is actually much more convenient. And in this basis, these few body operators are actually usually sparse. So it's naturally sparse. So for example, if you're looking at just a particular operator of sigma iz, sigma jz, right, as an example, so then this actually is already in this operator basis. Actually, only one of them is non-zero. So this is actually already a basis vector because this is equal to sigma, basically, as we said, right, identity on all the other qubit with the sigma z on the I and j. Right, so this is I and j. So this is actually already one of the bases. It corresponds to, gamma 1 equals to gamma 2, all the way gamma n equals to 0, but gamma I and gamma j equals to 3, right? If 3 correspond to the z. So it's actually already one of the bases. And if you have, for example, this Ising Hamiltonian we just talked about, I'm just going to write it here. Sum over ij, jij, sigma I, z, sigma jz. So here we have basically about n squared different coefficients, n squared different terms, because each of these is already in the operator basis. So that means instead of having 4 to the n coefficients here, we only have n squared of them, which are non-zero. All the other ones are just simply 0. Right? So this is a more convenient basis to represent these few body operators, or any Hamiltonian made of few body operators. Running out of time, I'm going to stop here, and we're going to continue on Wednesday. Yep, see you there. Have a good one.